Howdy, we're Team 33, Precision Drone Landing.
This project has been sponsored by Dr. Kevin Noka, and our advisor is Andrew Miller.
So with increased usage of quadcopter drones in land space data collection, automatic maintenance inspection, disaster rescue, and other applications, the demand of maintenance and management of drones as fleets emerged as drone system users attempt to increase overall efficiency. To accomplish the demands of automatic maintenance of drone fleets, the most important procedure is the successful capture of a drone in a landing bay. As the name suggests, Precision Drone Landing project aims to create a guidance system capable of making minute adjustments to the drone's position during its landing procedure. With the variance of landing position eliminated, maintenance devices can perform data retrieving and charging tasks automatically to increase operational efficiency as well as reduce costs.
In terms of approach, this project has been divided into 3 different categories with 4 main steps. In terms of navigation, there is divided into the initial GPS heading navigation, which guides the drone into the position which near to the platform. Secondly, the image recognition will capture the sign printed on the landing platform to make the precise landing. In the flight control part, the quadcopter drone is controlled by an automatic flight control system with the SDK app and also with the Bluetooth, which receives the guidance data from the Raspberry Pi. And finally, when the drone is landing, the platform has a electromagnet attraction components which to secure the drone's position. To enable the image recognition guidance process for a precise landing, initial guidance based on GPS coordinates and heading data is necessary. The GPS coordinates and the rotation reading of the landing site will be pre-built into the flight system of quadcopters. When the stage is finished, the initial guidance will lead the drone into positions near to the landing site at the height between 0.5 to 2 meters and align with the site prepared for image guidance. In terms of accuracy, GPS reading is reliable within accuracy less than 1.1 meters for both longitude and latitude. The error between magnetic north to true north is between 0.21 to 0.35 degrees at College Station, Texas, indicates that there is no adjustments required for the rotation data.
So once the feature from the navigation system returns the drone somewhere near to the landing site, the image processing system is then activated. So how it works is the image processing captures the image of the blue star through a process of key point matching from a set of the desired images that has been uploaded into the system. And then using the area of the image captured, it can then compute the altitude along with the feedback for translational units like longitude and latitude or the correct orientation. And once computed, the image processor will then send feedback to the flight controller. As of current, the accuracy in the image detection will run from 5 to 20% in error with increasing heights. The altitude measures with less than 2% inaccuracy, and the translation units of the X and Y coordinates will measure less than 15% error inaccuracy. And on the right, bottom right image, it shows the feedback outputted from the camera to the flight controller. Next image. In this video, it will show a better explanation of delay of 2 seconds where it captures the landing point and use it and fly the drone correctly.
So in order to achieve automated flight, GPS waypoints are used relative to the drone's current position. While the goal of the project is to improve upon current GPS accuracy, a series of waypoints can be issued and the drone's position can then be verified by the image processing subsystem to confirm whether to land or to provide another adjustment. And then in this video, this was an automated flight that we created with the drone, essentially in the flight control app that we have on an Android device. I wrote a mission that tells the drone to move. This is just demonstrating automated flight, but it tells the drone to move 1 meter in the latitude direction and then 1.5 meters, or well, excuse me, 2.5 meters back, 1.5 meters from the home point. This is not a final test. This is really just demonstrating automated flight. As you can see, there's pretty significant wind interference. Most of the days that we actually went and flew were fairly windy, which definitely affect the precision of the drone's movements. You can see it kind of like jerking around as it flies, but ultimately they didn't end up having a massive effect. And so then whenever we actually get into how are we controlling the drone, over here on the left-hand side, this is an image of the app that is used on the Android and then connected to the remote controller, which can then send data to the drone, essentially telling it what to do. That all the computations are running on the app, and then the controller is really just using an RF channel to actually transmit that data. And then over here on the right-hand side, this is a simple Bluetooth terminal. It really just allows us to open a port on the Raspberry Pi and on the Android so that we can then send data over Bluetooth. And a large issue that we were having was in integration of these two systems because we have two separate apps that need to communicate data. So on this next slide, you can actually see I implemented that Bluetooth terminal and merged it into the Android app so that we could access that data that was being communicated from the Pi in the flight control app for analysis and then for the issuing of flight commands. So over here, this is that interface for over here on the left, this is the interface for the Bluetooth app implemented inside the Android or the SDK app. And then on the right-hand side, this is actual data coordinates coming in from the Raspberry Pi being accessed inside the drone app. So essentially how this works is the image processing subsystem sends a string containing the distances in the X and Y directions by which the drone is off-center to the mobile Android SDK via Bluetooth. The Android device translates those distances into flight commands to center the drone above the landing site, and the device is permanently controlled to the drone's connected to the drone's remote controller, which then sends the necessary flight commands to the drone through an RF channel. Now, an issue that we had in doing this project was actually maintaining that Bluetooth connection. So as you could see in that user interface that we integrated into the drone app, there was a Bluetooth connection established between that and between the drone and the Raspberry Pi, or the Android and the Raspberry Pi, excuse me. But then whenever we back out and go into actually implementing a mission on the drone, the channel would actually fail. So essentially if that connection would stay online as the drone is still flying, theoretically this project would have been, we weren't able to keep that connection going even whenever we're not backing out of the whole app, it's really just backing out of the Bluetooth part of the app. Essentially because that connection couldn't stay up. We weren't able to fully communicate while flying. It was really more of these separate test flights and then testing the communication while it was actually connected instead of whenever it was disconnected, of course.
So once the landing is finished, the existence of the quadcopter will be confirmed by the weight sensor mounted beneath the platform to activate the electromagnets. Once the attraction system is engaged, electromagnets will secure the drone's position to accomplish the objective of the project. In terms of performance, the weight sensor has a sensitivity of 0.1 kilograms against the drone's mass, which is 2.0 kilograms, which means it's capable of detecting the drone's existence without any air readings. Two of the magnets each provide 250 newtons of attraction with effective range of 4 centimeters.
That's our presentation. Thank you very much.